Hello. This is Nicholas on this lovely Thursday afternoon, wanting to talk to you today about a video I'm really excited to make on the true second derivative test. Now, a lot of times this is taught in a single variable calculus course as just in terms of concavity, right? In terms of the function, right? Concave up, local minimum, concave down, local maximum, right? And then obviously right here is a critical point. The derivative is 0. Now, I want to generalize this to n dimensions, right? Because this only works, the single variable calculus case only works with functions that have one input and take that to one output. And even further, this is kind of a sequel to my last video, because even further, the video that I just did about the second derivative test in quadratic forms really only works, at least in terms of what I discussed, really only works for functions that take two input variables to one output variable. In other words, functions of the form z equals f of x, y. Today I'm going to talk about then functions of the form, say, x sub n plus 1 equals f of x sub 1 to x sub n. And I'm going to generalize this with the help of my friend, linear algebra. And really, I think this is somewhat unexpected, but it's really very elegant. I think if you have watched the previous video on the quadratic forms, you'll see just how massive those Taylor polynomials got, right? So on the one hand, we thought of the generalized quadratic approximation for an ND function of f at the vector a, right? And that looked like up to the second term, t sub 2 of the vector x is equal to f of the vector a plus the gradient of f evaluated at a times the vector x minus the vector a plus 1/2 times the vector x minus the vector a, dotted with the Hessian matrix evaluated at the vector a, matrix vector multiplied with the vector x minus a. Now, if you're at a critical point, that means that the gradient of f is equal to 0. We set the gradient of f equal to 0 for critical points, and so this term does go away. And now, what we're really left with, right, this is constant, right? This is a constant. So really what we need to consider here is this second term right here. This is kind of, we can ignore this, it's a constant. And so we said, well, we need to determine criteria for when this second term is positive, right? If this second term is positive, we think of this kind of like positive concavity, right? And then we can get a local maximum or a local minimum. And so we looked at the determinant of the Hessian matrix, and we did some things with the quadratic formula. But all of that really worked for R2. And even furthermore, remember that when we actually expanded this out in the case of in the case of z equals f of x, y, it got pretty nasty, right? Because there's a lot of notation hidden here, right? This right here is the partial of f with respect to x, comma, the partial of f with respect to y. And then this matrix right here is 2 by 2, and it's got all possible second partials of f. And so there's a lot of notation there. And if you remember, the constants, right, they were 1 over 0 factorial times f of, say, x naught, comma, y naught. And then we got plus 1 over 1 factorial, plus 1 over 2 factorial, and then we got a 1, 2, 1, right? This happened to be here, the second partial of f with respect to x, and then this happened to be the partial of f with respect to y, and then with respect to x, and the partial of f with respect to y twice. And we got some other stuff, but loosely speaking, you see that actually the Pascal's triangle shows up in the quadratic approximation. And if we were to continue, we'd end up getting 1, 3, 3, 1. And in other words, to get these coefficients, we need Pascal's triangle. And even furthermore, if we were to generalize this to a function like w is equal to f of x, y, z, then we'd need Pascal's pyramid. And even further, I mean, you need Pascal's hyperpyramid, where each layer would be formed by Pascal's pyramid, and algebraically can get pretty yucky pretty quick. So what we need is a new method to think about this. And what I'm going to propose is that we use the Hessian matrix, right? So, and it actually turns out to be just incredibly simple, because if I take the eigenvalues, of the Hessian evaluated at the vector A, and if they're all positive, we can think of this as positive concavity, a local minimum. If they're all negative, then we can think of this as a local maximum. If they're mixed, then we have increasing in one direction, decreasing in another. We have a saddle point. And if we have some, or if we have at least one, at least one eigenvalue that is 0, inconclusive, right? So now I'm going to I do have a video on eigenvalues with the Fibonacci sequence, but I'm going to take a step back and talk about eigenvalues just for a minute here. And everything that I've learned about eigenvalues is from Through Blue, One Brown. So really, I would strongly encourage you to check out his linear algebra series. In essence, though, eigenvalues come from the equation, the matrix A times the vector V is equal to lambda times the vector V. Now let's talk about this equation. The vector V is the eigenvector, and the scalar lambda is the eigenvalue. Now what does that actually mean? Well, the thing that you have to remember is that A is a matrix. A is a linear transformation. And you can go back to my video on what is a matrix to convince yourself of that. So what this equation is saying is that when I have a linear transformation, say this is in 2D, just for the case of me drawing it, and we consider a point in space, which is really, we could think of it as a position vector with its tail at the origin. Now, if I apply the linear transformation to this space, right? So right now, grid lines are parallel, and they're evenly spaced, say, by 1. Now, the linear transformation keeps grid lines parallel and evenly spaced, and the origin stays fixed, but it takes the vector to another vector, right? It might take the vector, after we apply the linear transformation, the vector might go up to, like, here or something. I mean, wherever. Whoa, I didn't know I could do that. So it goes up to, say, there. It doesn't really matter where. Now, some vectors move to different vectors, right? Like that blue vector. Like that red vector. But as it turns out, sometimes in some linear transformations, there are vectors that after you apply the linear transformation to the space, the vector lies on its span. In other words, it is just a scalar multiple of the original vector. In other words, this blue vector is parallel to the black vector. It lies on its own span, and what I mean by span is all possible, quote, linear combinations of one vector. If you're talking about a linear combination of a singular vector, that's just a line, right? That would be this line that would extend throughout R2. And so we call those vectors that lie on their same span after the linear transformation is applied the eigenvectors. And the factor by which I multiply this black vector to get this blue vector is the eigenvalue. It's a scalar. Now, if I look at the eigenvalues of the Hessian matrix and they're all, say, positive, we have a local minimum. And now, why is that? Well, the eigenvectors are some linear combination of my standard basis vectors. So I'll do these in a different color here. These are my standard basis vectors, I hat and j hat. And so if I can go in some arbitrary direction, it doesn't matter what the direction is because we're not even looking at the eigenvectors, just the eigenvalues. If I can go in some arbitrary direction and that vector, in this case the eigenvector, behaves such that it's just a scalar multiple of the original vector, and let's say the eigenvalue is positive, then what that means is if I go a little nudge in any direction, then the functional output, which we could think of in this case as the blue vector, right, it correspondingly goes up, right? If I go a little nudge in the input, there's a corresponding little nudge in the output. And it's a positive nudge, right? The nudge goes up because we have a positive eigenvalue. And then likewise, if I have a local maximum where the eigenvalues are negative, what that means is that the farther I do a nudge in the input, the opposite happens to the output, right? So if I go positively in the input, the output goes negatively. And what that means is that in any arbitrary direction, the function is going down. So like, for example, a downwards paraboloid, something like that, and we have a local maximum up here. In the case of a local minimum, the function would behave like ax squared plus by squared. And we would have like an upward paraboloid in the case of 3D. We'd have a local minimum right here. So eigenvalues, and this, by the way, this is exactly what you're doing in the single variable case. So let's look at why this is the case now. If I do a little algebra here with AV is equal to lambda V, you normally don't calculate eigenvalues from this expression. You'll bring this over to the other side. AV minus lambda V equals 0. And now this is matrix vector multiplication. This is scalar vector multiplication. So what I'm going to do here, this is kind of awkward, right, to have 1 here but not here. So what I'm going to do is I'm going to make this, I'm going to essentially multiply by 1 in a matrix form. I'm going to multiply by 1 in the form of the identity matrix so that I have lambda I V, where I is the identity matrix. I'm going to factor out of V to get A minus lambda I equals 0. So what this means is that, well, of course, in the case where if the original vector is 0, then, of course, any 0 vector is an eigenvector, right? But that's kind of a trivial case, so let's ignore that. If A minus lambda I equals 0, then, of course, the determinant of A minus lambda I equals 0. And this right here is the equation for how you calculate eigenvectors. Now, if you look at this, though, this is really very simple because let's say you've got a matrix A. Let's say it's 1, 2, 3, 4. And you know what the identity matrix is in R2, right? In R2, the identity matrix is just 1, 0, 0, 1. So if you do that minus lambda times 1, 0, 0, 1, you just get the matrix 1 minus lambda, 2, 3, 4 minus lambda. So all you have to do to calculate, and you set this equal to 0, so the determinant of it equal to 0. So all you got to do to calculate eigenvalues is just look at this matrix, subtract lambda along this main diagonal here, and then you're going to get a polynomial equation. You're going to set lambda equal to 0. So, and this is exactly what you're doing in the single variable calculus case, except it's kind of trivial because let's say you've got f of x is equal to x squared. Then, you know, you find critical points, right? F prime of x equals 2x. We set it equal to 0. We get x is equal to 0. We look at the Hessian matrix, but of course the Hessian matrix for a single variable function is just the second derivative. So that Hessian quote matrix is just the number 2. And And so the eigenvalues of that matrix, well, they're not very interesting at all, right? It's just 2 minus lambda, the determinant of that equals 0. And of course, then lambda is the second derivative. But realize that that is actually what you're doing in the single variable calculus case. The second derivative test isn't so much about the second derivative as it is about the signs of the eigenvalues. So now let's do an example to kind of cement this all together. Let's consider f of xy equals x to the fourth plus y to the fourth minus 4xy. So, of course, we first need to find the critical points, which is done in the usual way, right? We take the gradient of f equal to 0, the 0 vector. So what's the gradient of f? The partial of f with respect to x is 4x cubed minus 4y. Partial of f with respect to y is 4y cubed minus 4x. We set that equal to the 0 vector in R2. And we get the equations. Well, we get 4x cubed equals 4y. In other words, x cubed equals y. And y cubed equals x. So what that means is that, well, how can we solve? We got to just solve this equation here for x and y. So I know x cubed equals y. What is x? It's y cubed, so y to the 9th is equal to y. And then we get y to the 9th minus y equals 0. So y times y to the 8th minus 1 equals 0. And so we're going to get, at one point, we're going to get y is equal to 0. And then in the other case, we get y to the 8th minus 1 equals 0. And since the Hessian matrix, if you remember, is symmetric, because the order in which you take partials does not matter, all symmetric matrices have purely real eigenvalues. And so really then the only y values that we need to worry about in this particular case are y equals plus or minus 1. Right, those are the only two values that solve that equation. And then now if y is plus or minus 1, well, first of all, if y is equal to 0, then x is equal to 0 by that equation. So one critical point is 0, 0. The next critical point, if y is equal to 1, well, 1 is equal to x cubed. And then so x would also have to be equal to 1. So we get the point 1, 1 by that equation. And likewise, we get the point negative 1, negative 1. Now, we have those three critical points. Now we need to test them. We don't know really anything about them other than the fact that the directional derivative is not a positive or negative at that point. So that's kind of where our test fails. Not so much that we know anything about them. It's just where our test fails. So now we go to test these critical points. We need to first come up with the Hessian for this matrix, or for this function. So right, the second partial of f with respect to x. So this is the partial of f with respect to x. Now I'm going to take the partial again with respect to x of that. I'm going to get 12x squared. Now, if I take the partial of this with respect to y, then I get just a negative 4. And that means I also get a negative 4 right here because the order in which I take the partials doesn't matter. And then the partial of f with respect to y, again, of the partial of f with respect to y, well, that's 12y squared. So now what that means is that the eigenvalues of that matrix, well, I just subtract lambda along the main diagonal, take the determinant of it, set it equal to 0. Really very simple. So 12x squared minus lambda times 12y squared minus lambda plus 16 equals 0. In other words, 12x squared minus lambda times 12y squared minus lambda equals negative 16. And now I need to just plug in these three critical points for each of those x and y. So if we have the case where we have 0, 0, well, we have 0 minus lambda times 0 minus lambda. We get a negative lambda squared. We get a negative lambda times a negative lambda. That's lambda squared is equal to negative 16. So we are going to throw that out because we're only going to get real eigenvalues. If we have 1, 1, well, 12 minus lambda times 12 minus lambda, it's 12 minus lambda. Oh gosh, I'm sorry. I messed up on my, because this is a minus, it should have been a minus 16 right here. I'm sorry. So that would have made it a plus 16. Yes. Because the formula for the determinant of a matrix is that minus that, and it was a minus 4 times minus 4, which is still a minus 16. My bad. I'm sorry. So now, okay, when I set the is x equal to 0 and y equal to 0, I get lambda squared is equal to positive 16. Lambda is equal to plus or minus 4. What that tells us is that we have mixed signs on our eigenvalues. We have a saddle point. We have a saddle point at the origin, 0, 0. Now, when x is equal to 1, y is equal to 1, we get 12 minus lambda squared is equal to 16. Again, without knowing what lambda, well, okay, I'll do it all the way. So we get 12 minus lambda is equal to plus or minus 4. It's taking the square root of both sides. So in the one case, we get 12 minus lambda is equal to 4. 12 minus lambda is equal to negative 4. So in this case, right, lambda is equal to 8. In this case, lambda is equal to 16. In both cases, though, lambda is positive. It doesn't really matter that they're 8 and 16 so much as it matters that they're both positive. If they're both positive, right, that means that we have a local minimum. So we have a local minimum at 1, 1. And then lastly, you're going to get the same thing for negative 1, right? Because negative 1 squared is 1, negative 1 squared is 1. You're going to get the exact same algebra. So we have we also have a local minimum at negative 1, negative 1. And I feel like this is a much easier way to grasp the true second derivative test in terms of the eigenvalues of the Hessian matrix. And so I believe with that,